Welcome back. In today's lecture, we will cover the aerodynamics of propellers and windmills. First, the propeller. A propeller is a screw-like rotating device which rotates to produce thrust. It has multiple blades. Each blade is an aerofoil with a leading edge, a trailing edge, a tip, and at the root it is connected to the hub. Let us consider a propeller in which the blade is in the horizontal position and is rotating at an angular speed of omega counterclockwise. Let's take the section of a propeller at a radius r from the axis. This looks like an aerofoil. It has a downward velocity and it has a forward velocity v, that is the velocity of the aircraft. Now, in a frame of reference fixed with the propeller, we can consider the velocities to be in the reverse direction, so that the resultant velocity vector to the aerofoil is like this. Now, this means that we have an aerofoil that is flying into a wing at a small angle of attack. This angle phi at which the wind is coming is more than the angle the chord makes with the horizontal direction, and so there is an effective angle of attack. We call the angle that the chord makes with the vertical as the pitch angle. This is the resultant velocity onto the blade. This is angle theta, which would be tangent inverse omega r divided by v, omega r being the vertical component of velocity due to the rotational speed of the blade, and v is the forward velocity of the aircraft. The angle of attack alpha then is theta minus pi minus beta. V divided by omega r is termed as the advance ratio. This is the ratio of the distance moved by the aircraft in one rotation divided by the distance moved by the tip of the aircraft in one rotation. Here capital R is the radius of the rotor blades. Let us consider the forces that they result. The air is coming to the aerofoil at a small angle alpha. Because of this, a lift results which is perpendicular to the direction flow, and a drag force results which is in the direction of the relative wind. Because of this, the resultant force on this propeller element is shown by this blue arrow. We resolve this resultant force into a component which is thrust-like, it is in the forward direction, and a component which is radial. This component of thrust can be determined from the lift component and the drag component. The radial component will produce a torque that will need to overcome by the engine that is revolving the propeller. The contribution to thrust from this figure we can see is L sine theta minus D cosine theta, while the contribution to torque would be the radial element of the force, which is L cosine theta plus D sine theta multiplied by the radius r at this location. The total thrust and the total torque are obtained by integrating this elemental thrust and elemental torque over the entire R from the root to the tip of the rotor blades. The L and D value will depend upon the velocity V, the location R along the blade, and on the density of air. The power consumed by the engine would be the torque time the angular velocity omega of the rotor, and the power delivered would be the thrust produced times the velocity. So that the propeller efficiency is power delivered divided by power consumed. We will establish here the need for twist on a propeller blade. Shown here is the relative speed of air with respect to the propeller, and this is shown by this green arrow. The angle that this velocity makes with the chord of the blade is the angle of attack given here. Now suppose we take a section of the blade at a different value of R. Let us take it at a smaller R than this picture that we have drawn. The forward velocity is the same, and because of this red arrow gives you now the relative velocity of wind at this section of the blade, which is at a location inwards of the earlier section at which the relative velocity is V. And so when we transfer it to the blade, this is what the relative velocity is. And you see clearly the effective angle of attack has decreased. So the blade would act differently than it was acting at that R. For a blade to be acting at its most efficiency, we need to keep the L by D ratio, that is lift to drag ratio, or CL by CD ratio, fixed at the optimum. And if we keep it to optimum, there is an optimum angle of attack that must be maintained throughout the length of the blade. And this is possible only if we twist the blade. We will twist the blade so that it is a higher beta towards the root than at the tip. Beta should increase towards the root. If we take a rotor blade, a propeller blade, the propeller blade has a very coarse pitch at the root compared to the pitch at the tip of the blade. The propeller blade angle changes from coarse to fine, from root to tip. To analyze the propeller performance, we do a similarity analysis. The governing laws are three that are important. The first one is the centrifugal inertial force, which would be mass times omega square L. So the scale factor for the centrifugal inertial force would be K rho, K omega square, K L raised to power 4. The streamwise inertial force is mass times the streamwise acceleration, which is V dV by ds, and that gives you a Kfi of K rho, kV square KL square. Similarly, the viscous force is the area times the viscous shear stress, which is mu dV by dN. And that in scale factors terms gives you Kf mu is equal to K mu Kv KL. From this, we establish the similarity rule that Kv by K omega KL should be 1 and K mu Kv divided by K rho K omega square KL raised to power 3 should be 1. From the first one, we obtain the pi number V divided by omega L. We use L as the diameter of the propeller and V characteristic is the forward velocity of the aircraft. The second parameter is mu V divided by rho omega square L cube. And you can see this is like a Reynolds product of Reynolds number and the first parameter that we obtained earlier. So any non-dimensional parameter or variable which is dependent should be a function of V divided by omega L and mu V divided by rho omega square L cube and the geometry including the pitch angle. It is conventional to take V naught, the velocity of advance, as the characteristic velocity, the diameter d of the propeller as the characteristic length, and then the independent parameter reduced to velocity ratio Ve is equal to V naught divided by omega d and Reynolds number rho omega d square by mu. Note that in some aviation literature, the velocity ratio is replaced by the advance ratio J, defined as the ratio of the distance moved by the propeller in one revolution to the diameter of the propeller. V naught divided by Nd, where N is in hertz, the number of revolutions per second. Thrust of the propeller is like a force, so K thrust is K rho Kv square KL square, and by replacing Kv by K omega KL, we obtain thrust as K rho K omega square KL raised to power 4. From this, we obtain the pi number. Thrust T divided by rho omega square d4 as the dependent pi, the dependent parameter, and thus the thrust coefficient is defined as thrust divided by rho omega square d4, and it should be a function of the advance ratio, the Reynolds number, and the geometry. The dependence on Reynolds number is rather low for large Reynolds number for which most propeller operate, so that the thrust coefficient is largely a function of the advance ratio for a given propeller with a given geometry. The typical performance curves, the thrust coefficient versus advance ratio look like this for different blade angles, for different pitch that we adjust. These are the propeller curves for a propeller numbered 58689, which uses Clark Y aerofoil. The torque Q at the shaft is the moment. So KQ is like K force into KL, and that gives you K rho K omega square KL raised to power 5. This gives Q divided by rho omega square d5 as a dependent parameter, and we define a torque coefficient CQ as Q divided by rho omega square d5, which should be a function of advance ratio, Reynolds number, and geometry. The power supplied to the propeller is torque times the angular speed of the propeller. So Kp in, the scale factor though for the input power is Kq times K omega, which is K rho, K omega cube, Kl raised to power 5. This gives input power divided by rho omega cube d5 as a dependent parameter and is called the power coefficient Cp as P in divided by rho omega cube d5. And these are the typical plots for power coefficient and advance ratio for the same propeller for which the torque coefficient curves were given in the earlier slide. The useful power from the propeller, the payoff delivered, is thrust times the forward velocity. So Kp out, the scale factor for power out, is K thrust times K forward velocity. And from this, we get a power coefficient, Cw dot is equal to power out divided by rho omega squared d4 V dot, which again should be a function only of advance ratio, Reynolds number, and the geometry, including the pitch angle. The propeller efficiency is defined as P out divided by P in. And if I put for P out TV naught and for P in Q omega, then we get this as Ct divided by Cq times the velocity ratio, or 1 by twice pi Ct by Cq into the advance ratio J. And for a propeller, we plot the propeller efficiency versus J. This is the kind of curve that we get for various beta, various blade angles, various pitch angles. All have about the same maximum efficiency. But the maximum efficiency is obtained at a higher advance ratio for a blade with a higher pitch. Now, let us see what happens when the forward speed of a propeller changes. That is, when the aircraft moves faster, the rotational speed of the propeller remaining constant. Here, the green arrows show the velocity vector with respect to the chord for a given forward speed v and a given rate of rotation omega at a radius r from the hub. Now, as the forward speed increases, the resultant velocity given by this arrow is now inclined at a different angle. When I transfer it to the aerofoil, the velocity comes here. This results in a lower angle of attack if no changes are made in the blade geometry. If the earlier value of angle of attack was optimum, then we must change the pitch of the propeller, pitch of the blade, such that the angle beta increases so that alpha gets back to its optimum value. This is the curve that we saw for efficiency versus advance ratio. And we like to remain here as the advance ratio changes. That means as the velocity increases, the advance ratio increases too, and so the value of beta must increase as was established just now. By how much is seen from this curve. At an advance ratio of 0.8, the beta at 3/4 of the radius should be 15 degrees for this propeller, but for twice the speed, that is at 1.6, beta should be more than 30 degrees. And at 3 times the speed, that is at an advance ratio of 2.4, it should be something like 43 degrees. So beta needs to change with advance ratio. This usually is accomplished by a mechanism, automated mechanism, which changes beta as the advance ratio increases. This is called a constant speed propeller, in which the rate of rotation of the propeller is kept constant. That is to get the engine running at the best possible speed throughout the journey, whatever be the forward speed. And so we have a constant speed propeller, but we change the pitch depending upon the forward speed of the aircraft.